Hi everyone. I hope everyone can hear me okay. And so my name is Timnit, and I'm a PhD student at Stanford in the AI lab. And I specifically do computer vision, which is a subfield of AI, as you all probably know. And today I was going to talk about part of my work, which relates to using all of these publicly available images that we have in order to extract useful insights for us. So predicting demographic variables, socioeconomics, voting patterns, and I wanted to talk to you about all the different things that need to happen in order to do this. So without much further ado, I'm just going to go to my slides, and I'm going to, there's a lot of detail, so I'm going to try to make it as succinct as possible so that we have enough time for questions. And, I'm going to gloss over a lot of stuff because there's so many moving pieces. And, during the questions, you can ask me more about things that you want to learn about in detail. So I'm going to share my screen now. Hopefully everybody can see this. Let's see if we can, let's see what we want to do. Here it is, share. And now we want to see full screen. All right, perfect. I hope this is working well for everybody. So I'm calling this, predicting demographics from 50 million images. Let me just keep time to make sure that I don't go on for too long, because I can talk about this for 2 hours if given enough time. So just to motivate this, the US Census spends at least $1 billion a year. The government spends at least $1 billion a year collecting census data. And this is a lower bound. We couldn't really find a source telling us exactly how much money they spend. They spend at least $1 billion. And we know right now is election season, so everyone is trying to figure out who's going to win. What are the polls like? Is it Hillary? Is it Trump? And basically, if you could predict the elections with high accuracy before they actually happen, it's safe to say that people would really be interested in that work. In addition to voting patterns and demographics, people also try to figure out crime rates in neighborhoods and what neighborhood attributes result to like high versus low crime rates, and they try to use these different predictions to figure out what to change about a neighborhood. So for example, there's some neighborhoods that decided that they don't want you to park at night because they figured out that people were using cars as a shield for crime. So, crime rates are one thing that people want to measure using whatever data they have available. And so we had an ambitious idea when we first started doing this, and this was over 3 years ago. And we said, how much of all of these things can we do just using computer vision alone and publicly available images alone? And we're not the first to have this idea. In 2013, there was this work from MIT that so what they did was they collected a data set of images, and all these images had attributes associated with them. So for example, for each image you have, does it look safe? Does it look like an image from a wealthy neighborhood? Does it look like it's unique? And the way they did this is they take 2 images and they crowdsource this, and they show people saying, which image looks safer, which image looks like it came from a wealthy neighborhood, etc. And so once they collect this data set, then they train an algorithm to just predict whatever the attributes of the data that they collected from the images. So whether it's a neighborhood is safe or wealthy or unique. But before I move on, let me tell you about another work that came out of Berkeley. They try to do a similar thing, but they take a different approach. And now what they want to do is they want to predict housing prices just from looking at images. And so what they do is they take different patches of images. So if you look at some of these photos, you can see that they have different patches of windows, for example, and they try to associate the properties of these patches to properties of houses that are expensive or cheap. So that some houses might have expensive houses in general might have like larger rooftops or larger windows or something like that. But all of these methods are very, very limited because they use global image features. And what I mean by global image features is that they don't identify specific objects in the image. They don't say, if you have an expensive car and a lot of greenery and X, Y, or Z in an image, then this image might come from a specific type of neighborhood. That's not how they do it. They say, let's look at images in general. Let's look at the global properties of images, and that global properties, and there are certain computer vision techniques that capture these global image properties. I have in my slides like GIS, CNN features. CNNs are convolutional neural networks. I'm sure some of you are familiar with that. So these features just capture global image patterns like color histograms or something like that. And you can't expect to get so much information about a particular neighborhood by just analyzing, global image features like color patterns and such. So we figured this calls for a different approach. And we said, we need to use object recognition technology in images to do this. And so if you have been following the ImageNet challenge, which is also it used to be run by our lab, every year the submissions have been getting so much better. And these submissions are basically algorithms that we have a certain data set, and it's a competition to do object recognition, object classification, let's say, in this case. And every year you see the error rates have been drastically decreasing. And now if I didn't have a bar chart for 2015, in 2015, these algorithms have started to be better than human performance, better than human error rates. So on the y-axis here is the error rate of these algorithms. So we figured, we have to use some sort of object recognition technology to do this. But then the question is, if you're going to use object recognition technology, then what objects in images do you use in order to predict demographic variables? So the question is, if you have a collection of images from a particular neighborhood or a city, what object do you want to recognize from those neighborhoods that you think will tell you a lot about the characteristics of that neighborhood, the crime rate or the voting patterns, or the income level or the education level or the race of its inhabitants, etc. And I'll give you a little bit of time to think about this. And we thought cars. Why cars? Because there are a lot of stereotypes about people who drive certain types of cars, right? And they might be accurate or inaccurate, but you make a lot of assumptions about someone just by knowing what type of car they drive. So for example, if you know that someone drives a Toyota Prius, which according to our analysis happens to be one of the most popular cars driven by people from San Francisco, you would make certain assumptions about maybe where this person lives, how much they make, because a Toyota Prius costs a certain amount of money, and maybe they're care about the environment, especially if they bought this right when Priuses started coming out, etc., etc. So you can learn a lot about a neighborhood by just looking at how many Toyota Priuses there are in that neighborhood. So this is the overall goal of our project: is take a whole bunch of images, millions and millions of them, detect all of the cars in those images, and using computer vision and using the information, that we gain about the cars that are located in all the neighborhoods, use that to figure out what kinds of people live there and what are the neighborhood's characteristics, etc. Now, there are so many steps to doing this that it's not very obvious that it would work. The very first thing you need to do is you need to collect training data. And what does that mean? So in order, what we're trying to do is we're trying to figure out what kinds of cars exist in all of the streets in the United States, according to images that we find from them, right? First, we have to do this. So in order to recognize all of the cars that you can possibly see in an image, you have to first create an algorithm that can do that. And in order to create this algorithm, you need to give it training data. You need to have labeled images with cars, with different kinds of cars that say, okay, this image has this specific type of car, this other image has this other specific type of car. And you need to do this for pretty much all types of cars that you might encounter in all of these neighborhoods. And so this is something that we call fine-grained image recognition. So fine-grained image recognition is the task of image recognizing different types of very, very similar objects. So let's say different types of birds, different types of trees, different types of dogs, and different types of cars. And these are very, very difficult to collect. So many times when people talk about artificial intelligence or computer vision or something, they're always just talking about algorithms like the object detection algorithms, object recognition algorithms. And even though these algorithms are doing very, very well, they all need training data. And it's very difficult to collect this training data. It's very expensive. And it's usually not scalable if you want to deploy these things in the real world, really, because you can't possibly, it's very difficult to collect training data for every single type of object that you might want to recognize. So this was a big challenge for us. And so here's an example of why it's very difficult. So first, how do you even define, when you have training data, you need to have different classes. You need to say, all of images of this particular type of car are class 1. They should be classified as one particular type of car. All of these other images from this different type of car, they need to be classified as this other different type of car. But so what does this mean? In our case, you have 2 examples of 2006 Toyota Prius and 2007 Toyota Prius. And do these look the same or do they not look the same? I think in this case, they look the same. We don't consider color to be a different attribute of a car. We don't care about whether or not the car has different colors. And so the first step in our analysis, and so here you see there are different types of Toyota Priuses, and on the left you see you have different, you need to see whether these are visually the same or not, right? So you have the ones in red that are still 2006 Toyota Priuses that look pretty much the same. And then you have the ones in the diagonal in blue that look the same as well, but different from the ones in red, right? Visually, their appearance looks different. And you have the one in green, which looks different because look at this. The grill here is different from these two. So these are the types of visual distinctions that we're trying to even capture with our algorithm. And so first we have to create what we call a class list, grouping different types of cars that are visually the same into one class, like this one and this one class, and then the ones that are different from like these ones, for example, into a different class. And so we have to do this for all cars that have been manufactured ever. And we decided we're going to limit it to all cars that have been manufactured since 1990. So this was a very painful process. We even have a paper on this, a crowdsourcing. We created a crowdsourcing algorithm to help us do this. And I'm not really going to go into that. If people want to ask me questions later, they can. But so this was a very painful process because before you even start labeling images, you have to first create a class list defining what types of cars are visually distinct from each other. So after we, and so this is just an example, like a brief example showing you, what kinds of car hierarchies there are in terms of naming terminology. So for example, you can have something like a BMW, that's the make of the car. And then you have the the model, which is 3 Series, 5 Series, etc. And then you have a body type. Here we have like a wagon and a sedan in the left, and then under that you have different kinds of cars that are differ because they might have a different year, like 2006, 2007, and trim. If for Honda, there's like LX, DX, etc. And so here at this level, you want to see whether they're visually the same or different. So in this case, you see that here there is a slight visual distinction. The bumper of these two cars is different. So I was never a car person before I started working on this project, but this was the kind of stuff that we had to pay attention to create an accurate computer vision algorithm. So finally, once we had our class list, we said, okay, how can we gather training data using the least amount of money possible? And what we said was, well, we should leverage existing e-commerce websites like Craigslist or cars.com, because what happens is when the images that are uploaded to their websites are uploaded by people who are trying to sell their cars. So when I'm trying to sell my car, I take images of that car and I tell you exactly what type of car it is. And this is basically training data. This is because what we need in training data is images labeled with the types of cars they contain. And so we do that, and we get images like this, and we clean them up a little bit using Amazon Mechanical Turk. So we get about 300,000 or so labeled images for that, using that method. But then, remember, what we are trying to do is we are trying to detect these cars, recognize these cars in images of neighborhoods that we have, right? Real world images, because our ultimate goal is to be able to predict demographics in these neighborhoods. And what images are we using to capture images of neighborhoods around the country? Google Street View images, because for each neighborhood, you basically have a whole bunch of images of that neighborhood. And so we can't just train an algorithm to detect cars in Google Street View images using images from Craigslist, because the image statistics of these two sources are very different, and you come across a problem that is called domain adaptation. And so that's another thing you have to do in order to fully utilize the labels that you get from one source to create an algorithm to detect an object in a different source. That's not something I'm really going to go into today, but it's another line of work that's very important for us. So, but now we have to collect car images from Google Street View, and this is really difficult because this is the kind of stuff you do. You show someone this kind of image like this, and you say, "What type of car is this? Tell me." And no normal average person can really tell you this. You need to find car experts to do this for you, and you need to pay them. So we came up with a UI to label this using a lot of car experts. And so finally, we have a bunch of training data to train our algorithms with. And most people kind of gloss over this step. That's really important. And that's why I spent all this time talking about it, because you can most of the time use off-the-shelf algorithms, but gathering training data is really what takes the most amount of time when you're working on these kinds of problems. So now we have a lot of training data, a lot labeled with images and cars in the images, and we can use that to train our algorithm and to test how well it's doing. So finally, we gathered 50 million Google Street View images in 200 of the largest cities in the US, in all of these different cities. And we detected all the cars in them using an algorithm, a very actually old algorithm called DPM, that it's ancient in these standards, but it was very simple to implement and very fast. So we thought, okay, we'll try DPM and see how it works, and if it doesn't work well for our purposes, we will use something that's state of the art. Back then it was RCNN, now it's something called faster RCNN. And this is really important because a lot of times people want to just look at the fastest, most recent, I'm sorry, not the fastest, but the most recent algorithm with the lowest error rate. to work on their application, but that might not be the best thing for you, because you might not care that much about a few percent of accuracy, but you might need to have a very simple, fast algorithm, because remember, we're trying to detect cars in 50 million images. And so for us, we can trade off a few percent of accuracy for to have something really, really fast. So and then again, so what we first did is we used DPM to, the first thing we did is we figured out whether there is a car in an image or not, any car. So this just tells you there is a car here and there is another car here. That's what DPM gives you. And then with a convolutional neural network, you can actually classify the car into one of over 26 different kinds of cars. That's what we did here. You have this type of car. We have a CNN, a convolutional neural network, and it tells us actually this car here is a Chevrolet Blazer, and this other car here is some other kind of car. So doing this, we created an algorithm, we trained an algorithm that detects over 26 different kinds of cars. So here's some of our accuracy. I'm not going to go that much into this detail. And so, for example, 26-way accuracy is about 31%. So that's really good for computer vision to be able to distinguish between 2,600 very, very difficult, hard to distinguish classes and get a 31% accuracy. At the model level, just that's distinguishing between an Accord versus Honda Accord versus a Honda Civic. It's much higher, it's 52%. Make level, that means BMW versus Honda versus Volkswagen, etc. That's about 67%, etc. Body type is whether it's an SUV or a sedan or a truck. And here is what we call a confusion matrix. You can see here, for example, we have of the percentage of cars that were extended cabs, how many of them did I classify as an extended cab versus something else? So you can see, the confusion is between very similar classes. So for example, extended cab and crew cab are both types of trucks. Minivan is, we say it's a minivan 84% of the time, which is pretty good. Yeah, so this is just to show you what it looks like. And here is the make level accuracy. We have, Acura and what is this? Tesla is all the way here. Just to give you a sense of how our algorithm is doing. And so now let's get to the interesting part, which is the results. So let's look at results in predicting demographics. Okay, so the question one is, how green is each state? Can we figure out how green each state is? So what we did is, okay, so for each type of car, we have metadata, like the price of the car or the average miles per gallon of the car in 2012, etc. And so we said, can we just calculate the expected miles per gallon of each city and try to figure out how green each state is? Just very simple calculation. And so we map out, based on our calculations, what we think the average miles per gallon is. So you look at California here. So using all of the cities in our data set in California, we try to figure out we just calculate what the average fuel efficiency is of California, etc. Here, we just use fuel efficiency here. And then here we have carbon footprint data that we got from the EPA, I think. And I think the correlation here was 0.67, which is a pretty good correlation. Just looking at the average miles per gallon, you can see the coastal cities are greener than the inland ones. In some cities, it doesn't make sense. Like here we get them very wrong, but here, for example, we get them right. So that was interesting for us to see. And a very interesting thing is that in our data set, Burlington, Vermont had the highest fuel efficiency. And I think Casper, Wyoming had the lowest one. And we found out that Burlington, Vermont was the first city to go 100% green. And Casper has the highest CO2 per capita emission. So it's very interesting. I think what we kind of how we interpreted this is to say that people who drive fuel efficient cars care more about legislation that helps their environment. So maybe they vote for legislation like the ones in Burlington, Vermont, that make them go green. And then the second question is, can we just look at one other attribute of the car, like the car price, to see what income segregation levels look like? So I'm not going to go into this math, but just, we use something called the Morton's eye statistic. It's a spatial autocorrelation measure. And so we find that just by looking at car price, we can map what are the most and least segregated cities in the country in terms of income. And then we can further visualize it. So we found that Chicago is the most segregated city. And we can look at here in red, you can see like clusters of expensive cars. And in yellow, you can see clusters of like, very cheap cars. And then here, in Jacksonville, we found to be the least segregated one. And you can see like there's very little clustering of expensive and cheap cars. So that was interesting. And then we then said, can we predict things like income? And so here what we did was we use all the car attributes that we have in our data set, like, the make, the number of cars per image, the average car price, the body type, etc. And we did ridge regression. So we trained a model to predict income from the attributes of the cars for each region. And so here is our results. Like here is our predicted median household income, and here is the actual median household income, and we have a correlation of about 0.7. Here's an example in Philadelphia where this is the actual median household income, and this is the predicted one according to us. And I'm just going to show you a whole bunch of results like this from now on. And then, what's interesting is to see like what, types of cars are highly correlated with income. And it's really interesting. Like the most highly correlated one is the percentage of foreign cars in a place. And, German cars, Japanese cars, etc., Lexus, and also, we have BMWs and stuff. That's kind of obvious. And then the most negatively correlated is, American cars, old cars. So if you see a lot of American made cars in a neighborhood in our image, or like a lot of old cars, then you are more likely to be in a lower income neighborhood. And then we said, can we predict voting patterns? It's election season, so that's an interesting question. And the answer is yes. Again, this is actual versus predicted. And at the voting precinct level, and here's an example here, for example, in San Francisco, we get this one. We get this one wrong. We incorrectly say it's a Republican precinct, but most other ones are Democrats. Here is is this Casper? Yep. We say it's mostly Republican, except we get some of these wrong. And here is, I guess, Bakersfield, California. And then, again, what is car attributes that are most highly correlated with Democrats versus Republicans? Well, it turns out that places with sedans have a lot of sedans have a lot of Democrats, and places with a lot of trucks in our data set have a lot of Republicans, which was very interesting to see for us. And then finally, we said, can we predict race? So if the answer was no, I wouldn't be sharing this with you. So yes, here are, examples for the percentage of white people in Chicago. So this is actual versus predicted. So you can see we can pretty much get most of it. And here is for the percentage of Black people in Chicago. Here is the percentage of Asians in Chicago. And then, again, we can ask the same question about what predicts what car attributes are most correlated with what race. I'm going to skip over this for now. And finally, can we predict crime rates? Yes. And here are, again, actual versus predicted crime rates for some cities. This is New Orleans, I guess. And again, this is a very interesting one. The most positively correlated car attributes with crime rates are number of cars per image and the percentage of vans in a zip code, which is really interesting because number of cars per image, I think that gives you the density of cars in a neighborhood, and probably like, you know, if you live in a lower income neighborhood, for example, there's a lot of cars, high density of cars, probably high density of people. And the van thing is, it's just very interesting, and we don't know exactly why. The high density of cars, that's something that people have studied, and they're trying to, like I said before, for example, get rid of your ability to park throughout the night, because they do think that cars, a lot of places with a lot of cars have a lot of crime, because people use the cars as a shield for crime. For example, like parking lots have a lot of crime. The final thing we did is we said, okay, can we now look at, predict the future, what's going to happen in the future? So Google Street View has this thing called time lapse. So you can see for a particular address, how this address changes over time. So here is New York City. I don't know if I think this is in Brooklyn. You can look at it in 2007, you can look at it in 2014, and you can see how drastically it has changed. And you can see, just by looking at this image, you can see that, you know, the income level of this place has changed, right? So we wanted to see if we could do this using computer vision and just looking at the cars. And so we did that for New York, and we basically trained, used our models that we trained to predict demographics for each year. And so here's what we found. We found that we did this just for the whole city, and that income levels dropped around 2009, and then they started going back up. We think, you know, the recession kind of starts here. This is very experimental. We haven't published this yet. So this is the kind of stuff that we're doing now, just to see if we can actually apply this to predicting things in the future before data is available. So my conclusion is that, you know, there are a lot of images in the world that we're just not using very much. People have done a lot of this kind of data mining stuff using text, social networks, etc. But we haven't done this using images. And, you know, there are so many images getting uploaded into the web that we should start doing this using computer vision. And I hope this kind of convinced you that computer vision is ready to be used in this type of work. And we'll call this, you know, computational visual sociology or something like that, where people haven't done this before, but we think they should start doing it. And that's it. Now I'm gonna open it back up for questions. Yes, so I'm not sure how to do this. Can you repeat the correlation between crime rate and cars? The audio went out for a second. Okay, yes, I can repeat the correlation between crime rate and cars. So I'm not gonna, I don't know if you want me to show you my slides, but yeah, so so the correlation between crime rate and cars, the interesting thing is that the two things that correlate highly, okay, yes, okay, I'm not, the two things that correlate most highly with crime rate seem to be the number of cars per image. So we use this feature as a proxy for you know, the density of cars in a neighborhood, and the percentage of vans in a zip code. So the percentage of vans thing is something that just came out of nowhere. We didn't really know why this was the case. The number of cars per image, the car density thing makes sense because I read up on this, and a lot of neighborhoods are actually trying to get rid of your ability to park cars throughout the night, because they say, like, criminals use cars as a shield to do crime, and so, like, they tried this in San Francisco, like, to get rid of some parking spaces. I'm looking at all of these. I'm looking at some of these questions. Okay, so no need for. Can you repeat? Oh, yeah. So Google Street View images are open source. So there is an API. They have an API to download images. You can't, you know, so you can download images. You can access images to do work on your research, but you can't publish those images. Like, you can't. So some people do research and they publish URLs images, but yeah, they don't can't publish them. Do you think it's feasible to detect Google Street View? So this question is, do you think it is feasible to detect license plate readers from Google Street View images? No, because they try to blur the license plates because of privacy issues. So I don't think you can do that. So if I show you some examples of my car data from Google Street View, you can't really look at the license plate because it's so blurry. And they do this on purpose. Like they have teams of people try and blur license plates. Like they have computer vision algorithms that do that. Let's see other questions. I'm reading through these questions here. Do you think there were any biases in how the data was interpreted? For instance, a city might have a better public transportation and lesser cars, but may still have higher crime rate. Yes, that's correct. That is correct. So the only thing we can do is, the only thing we know for sure is that we can predict certain things like crime rates in certain places using the cars in those places, right? So that we know. So I can show you, hey, we predicted crime rates using cars in these places. And I can look at the weights that my model places on different attributes of cars. And so it could be that for certain cities where that have just a very different distribution of cars from what we trained on, that this method might not work. But overall, the accuracy of our predictions is pretty high. So yes, for sure, there might be biases in how the data was interpreted. How did you scroll through Google Street View to run images through your model, CNN? This one, I'm not quite sure what this question says. So what we did was we used their API to collect a lot of images, and then we, for each image, so like I said, we had collected a data set of cars to use in training our CNN. And so once we collected our data set of cars, so for the input for the CNN will be, an image, and the output would be, the type of car that the image contains. So once we trained our CNN, on cars, now we just test it on Google Street View images. We run it, right? So we just give it an input image, and remember, first we crop out the parts of the image that we think contain cars, and that's not done with a CNN. That's done with the other algorithm I talked about called DPM. So once we crop out the part of the image that we think contains a car, then we input that into the CNN so that it tells us what type of car it contains. What papers, sites, or other references would you recommend for getting more details about the subjects covered by your research? I recommend the overall field of fine-grained image recognition. And so Jonathan Krauss in my lab, who just graduated, has done a lot of work in that, and he's also my co-author. I recommend domain adaptation works, which I didn't really cover here, but it's very highly relevant. I recommend MIT Media Lab Naik, N-A-I-K is his first name, I forgot his last name, his work, which is very related to mine. And I recommend, just for general computer vision, CVPR is a good conference. And so yes, those are, I think, the things I recommend. I might write more on the chat instead of just saying stuff about. What is an approximate cost of a project like this, and what was the most expensive part? Yes. Yes, so this is something people really gloss over. And the most expensive part of this was labeling Google Street View images. So this is why we labeled web images, like from Craigslist and from cars.com, because labeling Google Street View images was so expensive. We have to hire experts at least $10 an hour. And you have to give them a random image and tell them to tell you what car this image contains. And we help them out with UI and example images and stuff, but you still have to do this. Even the fastest people, I think, could maybe do one car per image. So And overall, we spent about $35,000 doing this project, and most of it, like 20,000, I would say, was spent labeling Google Street View images, and the rest was spent like, collecting bounding boxes, which means like having people draw a box around each car in an image for training data, and also cleaning it up. Like, for example, if we have images from Craigslist.com and that we think is images of a car, we want the images only of the outside of the car. So those kinds of things also cost money. But by far the most expensive part was labeling Google Street View images. Did you do it per street, per GPS grid? So we collected images every 50 meters. And so we collected, we first said we want to collect images for this GPS point, this GPS point, and all those GPS points were every 50 meters. And so when we aggregated the car attributes to train our model to do demographic prediction, we did it, for the segregation analysis, for example, we did it per GPS grid. For voting, we did it per precinct, voting precinct. And for like other things, we did it per zip code. Detecting things about the license plate readers. I actually meant detecting the automatic license plate readers, which are typically the high-speed cameras. Is it possible to detect these cameras from Google Street View images? Detecting the automatic license, which are typically the high-speed. I still don't understand your question. Oh. High-speed cameras mounted on police cars or on objects like road signs and bridges. Oh, so you're saying that if you had a bunch of police cars, could you detect the high-speed cameras on police cars? I haven't seen like how big they are, so you could potentially train an algorithm to detect these if you have lots of training data, but I doubt you can. I don't know how big they are, so I actually doubt that you could reliably do this because they might be so small. Yeah, I'm not sure. I don't know if you can do it because they might be too small to do. Yeah. So I don't know if you can do it from Google Street View images because the car is like the resolution is already so low. But in order to do this, you first need to have, so you first need to detect this is a police car or whatever. Like you first need to reliably do that, right? And then on top of that, you need to reliably detect where the camera is. So this seems like a two-step process for me. You might have very high, like a false positive rate, because you might confuse it other cars like that have something on top of them for this. But yeah, I would just try it out and see what happens. But yeah, you first need to reliably detect police cars, and then you can detect the stuff on top of them. All right, I think we're kind of over time. So thanks everybody. Thank you, and I hope you have a good rest of the conference. Thanks. Excellent. Thank you, guys. Bye.